Welcome back everyone to this fifth week of lecture of the lecture series on NPTEL course Principles of Synthesis of Polymers. So, if you recall what has gone on in the last week, we had started with talking about radical polymerization, that was a continuation of the previous week, and we were talking about different aspects, for example, the initiator efficiency, how it can be determined, and also how as a function of temperature the rate of polymerization may or may not change depending on the kind of initiation that you are using for synthesizing the polymers. And afterwards, we started talking about chain copolymerization reactions. We introduced the principle of copolymerization. So, there was a model called terminal model that we used in order to determine the expressions for the analysis of the reaction, the kinetics. So, and from there we also defined things called reactivity ratios of the monomers. We only limited our discussion to the reaction between a reaction mixture of copolymerization in which there are only two monomers, not more than two monomers. And then we also talked about instantaneous copolymer composition, when you have a very slight conversion from the starting monomer comonomer feed composition. And afterwards, we argued that the comonomer feed composition will drift as a function of time, because both the monomers do not have the same reactivity, they do not add to the polymer chain, to the growing polymer chain with the same propensity. So, ultimately what will happen is that the more reactive monomer will enter the copolymer to a more extent, to a higher extent, and leaving its concentration to be depleted into the comonomer feed mixture, and hence the comonomer feed mixture, the composition will drift with conversion, and accordingly the composition of the copolymer also will drift with conversion. We also tackled that, and finally, we talked about microstructure of copolymers. So, the sequence length distribution. So, you have two monomers M1 and M2. Now, depending on whether you have an alternating, perfectly alternating, or what you say as ideal, extremely or what you call as extreme behavior of alteration, or you can consider moderate behavior of alteration. Extreme behavior of alteration is R1 equals to R2 equals to 0, both the reactivity ratios are 0. So, you have perfectly alternating copolymer, completely non-random, and if your R1 and R2 are less than 1, but close to 0, then you have close to being perfect alternation, but it is not exactly perfect. And from there we determined how the sequence length distribution will vary, and we showed from the analysis that even triads, tetrads, M1, 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 triads, M2, 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 tetrads, for example, those are also present in a very small quantity, because it is not a perfectly alternating copolymer. So on and so forth. And afterwards, we started talking about, towards the end of the last week, we started talking about the leaving polymerization, leaving chain polymerization, and that is also the topic of today. So, we continue talking about leaving chain polymerization today also. So, if you recall the discussion of the last class of the previous week, we told that although the topic is quite general, leaving chain polymerization, so that should include say cationic, anionic as well as radical, but we are concentrating only on radical chain polymerization, which we are making into a leaving version. So, that is also, there is also a reason for that, because we consider the leaving radical chain polymerization to be the most important of all the leaving chain polymerizations, because radicals, the substrates are less selective as far as reactions in a radical pathway are concerned, because the intermediate radicals or the propagating species, the radicals in the propagating species could be stabilized, whether you have an electron donating group or whether you have electron withdrawing group, both ways, both can stabilize that radical. However, if you have an anion or a cation in a propagating species corresponding to an anionic or cationic polymerization respectively, that is not the case. So, if you have a electron donating group present, then it will destabilize the anion. So, that would mean that particular substrate will be reluctant to undergo anionic polymerization, it will rather undergo cationic polymerization, and vice versa. So, that means that cationic and anionic polymerizations, these principles cannot be, so for example, anionic polymerization, you try to make it leaving. Typically, many of the anionic polymerizations are leaving, because when you have this negative charge propagating in the species, so they can actually interact with the solvent, and then the negative charge could be taken off from this species. That is one of the ways in which the dead polymer could be formed. This does not happen all the time. Your solvents are typically non-polar that you are using. So, for all practical purposes, many of these negatively charged species that you generate in your anionic polymerization, many of these systems of anionic polymerizations, they will be basically living polymerizations, because the negative charge that you have generated generally is not taken care of or quenched in the under the reaction condition. So, those things we are not discussing. Say for example, if you are talking about anionic polymerization, applications will be limited, because not all substrates can be subjected to anionic polymerization. Same is the case with cationic polymerizations, but that is not the case rather with radical polymerizations. So, that is why we started talking about leaving radical polymerization, the most important of the leaving chain polymerizations of all, and we will restrict our discussion to only leaving radical chain polymerization in this particular course. So, to recall, we told that we need to have a propagating species, or in this case the propagating radical. You want to increase the lifetime of this, you want to stabilize this. So, you actually create a dormant species which will mask the radical, and the way you create this, there could be two pathways. One is reversible termination, and another pathway is reversible chain transfer. So, general scheme that we had drawn for the reversible termination. So, the general scheme is like this. You had, this is a recollection of what we had taught the previous week, something like this. So, you have an initiator which instantaneously dissociates to form these two radicals, and one of them is stable, or you can also call that as persistent species, that cannot initiate polymerization, but the other radical is reactive and that can initiate polymerization with the monomer. So, several of the monomers can add and it can create say RMN dot. Now, this could go to bimolecular termination. However, this is captured in this kind of reversible reaction with Z dot to produce RMN Z. This is the dormant species, and this equilibrium constant of this reaction is very important, because this concentration of RMN dot should not be too low, because if it is too low, then this propagation rate will be hampered, and if it is too high, then the bimolecular termination will become predominant. So, the idea is that you want to stop all the chain breaking reactions, So, be it termination through coupling, disproportionation, or it could be chain transfer also. So, those things you want to stop. So, this is the overall aspect of reversible termination, because you are terminating this growing propagating species in a reversible way, and this particular species you probably can isolate after, and once you isolate, you can add another batch of monomers. Say you are adding a monomer 2, and so M, let us say you are putting A. So, another monomer you are adding, and then you again add your initiator. So, basically this is your initiator. In this case, this was the initiator. So, this becomes a macro initiator, and generally you can use a catalyst to dissociate this, to activate this initiator to dissociate. So, that catalyst you will use here again, and afterwards. So, this is basically similar to this, but it is a macro version of that. So, macro initiator, and then you can add the molecule of A, say A number of units, and then again Z will be there at the end. So, this is how you can create specific composition of block copolymers, and So, we had already talked about one of the processes, reversible termination, which is ATRP, atom transfer radical polymerization, and this atom transfer radical polymerization, basically the RZ is your alkyl halide you are using, and you are using a copper halide, cuprous halide as the catalyst, and this will reversibly. So, this will actually, what will happen is that in a redox pathway, this will activate this thing, the RBr, electron transfer will happen, and the bromine transfer will also happen to CuBr. So, this is atom transfer, that is the name that it derives from, and you will have CuBr2, so on and so forth, and this R dot is this R dot, and that can create your RMN dot, and this Z dot is this. So, basically this is not a radical, but this is a persistent species. Now, this RMN dot could be reversibly terminated by the reaction with this CuBr2L ligand RMN, and this bromine again will be transferred here, and it will form back CuBr. So, it is a catalyst because CuBr is formed back at the end, so on and so forth, and you are using a nitrogen based ligand to stabilize this thing, in a way to solubilize this thing in the particular organic solvent that you are using. So, one thing that remained to be discussed was, if you are looking at the molecular weight distribution xw by xn, because this into m0 is mw and this into m0 is mn. So, mw by mn is your PTI. So, this is approximately equal to 1 plus 1 divided by xn bar. So, this follows a what you call as Poisson distribution, and if your xn bar is very high, then for all practical purpose this PDI is very close to 1, and that is something that happens because you initiate all the initiator all at once, it will dissociate to form R dot, and not only that, this R dot, I mean this will initiate the polymerization, and that all the chains that will start to grow, they will start to grow at the same time, and they will grow for the same length of time. So, that gives you a very narrow molecular weight distribution. And we also discussed one example of ATRP. So, we will just also talk about one more example here. Again, if we go to the PowerPoint, we will talk about one more example here. So, this is so if you look at the PowerPoint here, this is the actually this is not the PowerPoint, this is the PDF of the particular paper that I am showing here, published in Nature Chemistry in 2012, multiphase design of autonomic self-healing thermoplastic elastomers. So, basically here the idea is that you have a core chain which is made of polystyrene, and which is basically a hard block because the Tg or the glass transition temperature is high, and then you create some brushes along the length of it. So, these brushes that you have, they are basically made of this particular polymer which has this long chain which increases the glass transition, which decreases the glass transition temperature, which means the temperature, the room temperature is basically higher than the glass transition temperature. So, this becomes more flexible, it is not in the glassy state, it is in more flexible state, but this is in a glassy state. So, you have a hard soft mixture in the system. So, what will happen is that from the solvent, if you precipitate it, the solvent evaporates, and this particular thing, the hard block, that will create cross links, and this phase is the soft phase. So, basically these cross links, these hard blocks will be dispersed in the soft phase, and they will cross link the soft phase. So, ultimately this material will be stiff because the stiffness will be derived from this hard block, but this material will be stretchable also because the softness will be derived from this soft block. And not only that, the soft block has hydrogen bonding interactions that are present, that are engineered into that. So, that means you can actually stretch them and the hydrogen bonds will break, and afterwards when you remove the applied force, they may come back to their original situation by self healing. So, if you cut the material also into two halves, when you put them back together, because of the hydrogen bonding interactions in this soft matrix, they can come back together. Now, this is the overall principle, but how do you prepare this kind of material? So, what they did is that they basically have styrene, and this styrene is copolymerized with this particular monomer. You see that here this is kind of an alkyl bromide, particularly suited for ATRP afterwards. So, with the azoisobutyrylnitrile thermal initiation due to the polymerization, and you control the amount of this. So, how much of this amount will be in the side chain will also be controlled. Now, this is a macro initiator now, and this macro initiator, you are reacting with a monomer which is this monomer, and that is an ATRP reaction. You are using copper 1. So, with this ATRP reaction, basically since these macro initiator, the reacting center which is masked by the bromine, that is at the side chain. So, at the side chain actually your chains will grow from this soft brush, and then ultimately you get this kind of architecture, and depending on how much of this moiety you are using. So, if you change the ratio, you will change the ratio of this, how much amount is there, and then if you control the ATRP to what extent this grows also you can control. So, accordingly you can prepare different kinds of materials which will respond differently to the stress and strain. So, you may make the material tougher, that means the material can actually stretch to a longer strain, to a higher strain, and also stiff enough because the material has this backbone which is your polystyrene. So, that means it is a kind of an elastomeric material, and this is also stiff plus they are stretchable. So, both the properties are actually present. So, this is an example in which your structure dictates the property. Along the way we will discuss more examples after, but this is the power of ATRP, that is the take home message from this particular paper. Okay. So, we go back to our discussion on the script. So, basically this is all that I wanted to discuss about ATRP. Now, we will briefly discuss another process, another different kind of technique that uses reversible termination in order to introduce these dormant species. So, another kind of living polymerization which is living radical polymerization, which is NMP, which is abbreviated as NMP, nitroxide mediated polymerization, that is why NMP. So, basically the process is the same. This was ATRP. For nitroxide mediated polymerization, your Z dot basically is nitroxide. So, those nitroxides are stable radicals because of the steric hindrance in the system. So, they can be present there in the system, from the initiator they will come out, and that these nitroxides then it can reversibly terminate the growing propagating species, but they are so stable that they cannot initiate the polymerization. An example should do. So, basically you can start with this particular molecule CH3 and then oxygen, nitrogen, CH3. So, if this material you heat up, so reversibly it can break and it will create two radicals. So, it will break here, So, half arrow means one electron moving. So, you will create these two radicals. One radical is this CH3, which is your reactive radical, which is your basically your R dot. Your R dot is this material. So, which is basically this R dot, and this Z dot is your nitroxide radical which will be created from here, that will be this. Remember, this is a specific example of a nitroxide radical. There are other nitroxide radicals also available. Now, this radical is stable because this is sterically hindered. So, it cannot initiate polymerization, but it can reversibly react with the propagating species to terminate the propagating species. This specific radical has a name tempo. You may hear this name, this is a very known name. So, basically this radical is 2266. So, this is one position 2, 3, 4, 5, 6. So, 2 position 2 methyls, 6 positions 2 methyls, 2266 tetra methyl 1. So, one position 1 you have the oxygen radical 1. So, this is piperidine moiety. So, this is piperidinoyl dinoxyl, sorry. So, piperidinoxyl. So, one position. So, this is the name. So, this is tempo. So, this is a stable radical. In many situations you will see that this tempo is used as the persistent radical for nitroxide mediated polymerization. So, basically the general scheme is something like that. So, you may have, let us say, a nitroxide like this. So, this is your initiator species which can decompose to create dissociate to create your nitroxide radical. So, what will happen is that you have R 1 dot plus O n R 2 R 3 dot. So, this is a nitroxide radical. The same way this can react with monomer and it can create this propagating species, and that can be reversibly terminated by this nitroxide radical to create this dormant species O n R 2 R 3. Okay. Now, what you could also do is that instead of taking only one initiator, I mean this initiator produces a nitroxide radical, what you could have is a bicomponent initiating system. So, bicomponent initiating system means you could, instead of this, what you could take is your normal thermal initiator, maybe say azoisobutyronitride you are taking. So, this along with that you have a stable nitroxide radical, you take it directly, because some of these nitroxide radicals are so stable they can be sold commercially, they are so stable. So, this is a bicomponent initiating system. So, a bicomponent system. So, what will happen is that this will dissociate and this will form the growing polymer chain. So, you have say RCH2 CY1 Y2. So, this is your propagating species. Now, this propagating species could react with your nitroxide radical reversibly to terminate this, so on and so forth. So, if it will terminate this and it will create your molecule which is like this. So, this is reversible termination. So, you will have RCH2 CY1 Y2. So, RCH2 CY1 Y2, and then you have O n R1 R2. So, this species is nothing but similar to this particular species here. So, this is the overall principle of, so this is the activation deactivation. So, this is the basically your reversible termination step. So, reversible termination step, we have now discussed two of the examples, ATRP as well as NMP. So, both of these living radical polymerization processes, they use reversible termination in order to generate your dormant species. So, these dormant species then can be reacted with another monomer, so on and so forth. So, finally, what we want to talk about is, so we have talked about reversible termination process through which you can make the polymerization leaving. So, one thing remains to be discussed, that is reversible chain transfer process. So, because we told that there are two ways you can make the polymerization leaving. One is reversible termination, of which we discussed two different classes of reactions, ATRP and NMP. Another is reversible chain transfer. So, this is basically raft polymerization that falls under this class. This is reversible addition fragmentation chain transfer. So, reversible addition fragmentation chain transfer. So, the overall reaction is, so you have a chain transfer that is happening, and through that chain transfer you are basically creating the dormant species, and that chain transfer is reversible, that is the idea. So, the dormant species is being created through reversible chain transfer, unlike in ATRP or NMP where the dormant species is being created through reversible termination. So, you basically have a raft agent which is nothing but this. This raft agent will be a thiocarbonyl thio compound, and you have your monomer that is reacting, a vinyl monomer, and ultimately the product that you will form is something like this. And again then at the end of it you have this thiocarbonyl thiomoiety. So, this can be used as a macro initiator to create another polymeric block after. So, a wide range of functional groups basically are tolerant to raft process. Say if you have acrylates, acrylamides, acrylonitrile, styrene, butadiene, so on and so forth, all of them can be used. So, typically the mechanism is something like that. You have an initiation step in which you are using your normal initiator. Your initiator is decomposing to I dot, dissociating to I dot, and that is initiating your polymerization with the monomer, and you have say a growing chain P n dot. Now, the second step is basically called a pre-equilibration step or reversible, it is a reversible chain transfer pre-equilibration step, where there will be a reversible chain transfer of this raft agent with P n dot. So, this P n dot can react with your raft agent like this, and it will create P n S Z S R dot. Now, this is your raft adduct radical, raft adduct radical. This is your persistent species that we are talking about here in this case. This is not reactive enough to react with the monomer itself and start propagation of the chains. So, basically it does not react with the monomer and transfer the radical and then start propagation. It will basically react with this polymer and create a persistent radical like this afterwards. So, it can go in this way or that way, both ways. So, this is a stable enough radical, so that it will not initiate the polymerization, and what it can do is that it can decompose in this way P n S Z double bond S and R dot. Now, this R dot is the reinitiating species. So, this R dot in the reinitiation process, this R dot could again initiate your monomer, and it can create say a polymer chain P m dot. Now, in the fourth stage there will be, this is the main chain equilibration step. So, this is pre-equilibration and this is the main chain equilibration step here. Now, in the main chain equilibration step your P m dot. So, this P m dot that has been produced from this reinitiating radical, reinitiating species, this will react with your this moiety. So, basically I will just draw this as this. Okay. So, this is the equilibration step which will establish an equilibration between these two species here and these two species here, and finally, then this P m dot and P n dot in the fifth step they could just add up to produce P m P n, which is your dead polymer. So, basically you have this kind of stabilized radical species which will create what you call as, this is your latent or this is your dormant species that is being produced, and this radical species cannot initiate the polymerization with your monomer. So, specifically say if you certain things you have to keep in mind, that this chain transfer agent, the concentration of the chain transfer agent that you are starting with, the concentration has to be much higher than the initiator in order for this reaction to occur in a proper way, in order for it to be living. So, this has to be higher. So, there will be better control of polymerization, and this thiocarbonyl thio compound that you are using here, this is your raft agent, right. So, the Z that you have, this Z has to be so chosen that it will not only stabilize the intermediate radical. So, the intermediate radical is basically something like this P n S Z S R. So, it stabilizes this intermediate radical, but also it helps addition to the C double bond S bond, and that is why this reaction, this particular reaction is indeed possible. So, Z actually promotes the addition of P n dot to C double bond S bond. Not only that, it also stabilizes this radical. So, that is the purpose of Z. So, you have to choose it carefully, and this R you have to choose it carefully, so that it is a good homolytic cleaving group, because afterwards it will cleave off and it will be acting as the reinitiating species here. So, if you want to create overall, say if you want to create a diblock copolymer, so what you have to do is that you can start with this macro initiator, because you first create this polymer with your chain transfer agent. At the end of it you have this moiety. So, this is your macro initiator, macro chain transfer agent, and this can now react with the second monomer of your choice with your appropriate initiator that you are taking, and it will create the polymer like this. Okay. Now, something that you have to keep in mind here for this particular reaction is that the choice of the monomers. So, which monomer to add first and which monomer to add second in order for a successful raft polymerization reaction. So, typically for this kind of reactions, when you are making a diblock copolymer, for example, what will happen is that initially you have an initiator, right. So, that will create 2 I dot, and then this initiator will react with your monomer 2. Remember, you have already you have already thrown your die. That means, you have already chosen your first monomer. So, let us say your first monomer was this monomer. So, you have chosen the first monomer. You could also choose this monomer first. So, that is very important, which monomer to choose first. So, once you have chosen this monomer, you have created this macro chain transfer agent through the raft addition fragmentation reaction, reversible addition fragmentation reaction. Now, you are adding the monomer 2, which is M2, and you are adding another initiator. So, what will happen is that this initiates the polymerization of the second monomer. So, it will create this kind of radical, the propagating species. P stands for polymerizing system. Now, at some point this propagating species can do a chain transfer with your macro CTA. That is very important. So, it can do a chain transfer with your macro CTA. So, I am just drawing here generically. So, P M1 whole n. So, this was your polymer basically. At the end of it you have this unit, thiocarbonyl thio unit. So, that this is your macro CTA. Now, you want to add the monomer M2 as the second block, but what happens is that initially when you have used the initiator, the second block will start to form the propagating species, say x number of empty units have come together. So, at some point this particular growing propagating species will do a chain transfer with this particular molecule, with this particular chain transfer agent or macro chain transfer agent. So, when it does that, there will be an equilibration like this. So, you have PM2x S Z. So, basically let me draw this in a so this is single bond. So, you have this, let me split it up into two parts. So, PM1 N, you have this. So, this is again a stabilized radical, and afterwards it can break like this. You have PM2 X and then you have S double bond S Z, and this will come out as your reinitiating species. Now, this reinitiating species can basically initiate your M2 monomer, and then ultimately you will have at the end of it you have a block of M1 followed by a block of M2, say M units. So, something that you have to keep in mind is that this particular monomer, that monomer 1 you have chosen in order to create the initial chain transfer agent. So, once this chain transfer agent has formed, this chain transfer agent should have a high transfer rate constant with the propagating species of the second monomer. So, that this reversible reaction can actually occur, it can go towards this site. And not only that, this PM1N, this has to leave in order to create the reinitiating species. So, the leaving ability of this polymeric species from this stable radical has to be higher or at least comparable to the leaving ability of this polymeric species. Then only you can have this kind of two blocks that have been that are produced in this particular system. So, this is how basically you can use raft process to create copolymers, block copolymers. So, we will complete the discussion on leaving chain polymerization in this class by giving you one more example of raft chain copolymer. So, we will go back to the desktop and we will show you the particular paper here. So, self-healing multiphase polymers via dynamic metal ligand interaction. So, what they have basically done here is that they have created this macro chain transfer agent. Now, this first reaction is basically your normal radical chain polymerization reaction, AIBN is your initiator. So, this vinyl 4-vinyl benzyl chloride that you are taking. So, you can take this component with respect to this in a certain ratio, so that you can introduce, you can control the amount of Cl, CH2Cl that is there, and then you are using this reagent in order to replace this Cl with this particular moiety, and you can immediately recognize, then this becomes a chain transfer agent as per our discussion before. So, this is thiocarbonyl thio moiety, basically this is trithio carbonate moiety. This can also be a chain transfer agent, you can have 2 sulfurs or 3 sulfurs together. And after that, what you can do in the second step is that you can put N-butyl acrylate. So, this is the raft reaction, actually you put N-butyl acrylate, since this is coming out of the side chain, you create a brush of N-butyl acrylate from this unit. So, it was here. So, you create a brush of N-butyl acrylate, and in this N-butyl acrylate moiety that you are taking, you mix not only N-butyl acrylate you are taking, along with that you mix another monomer which is of this variety. At the end of it you have an imidazole moiety. So, if you take a certain ratio of butyl acrylate to a butyl acrylate which is functionalized with this imidazole moiety, then in that particular ratio they will add to the side chain in the raft polymerization. So, this here if it is M and here it is N number of units, this M and N you can actually control by taking the monomer mixture in that particular ratio. So, this becomes another macro raft agent, but the idea here is that you have created a polymer with this kind of side chain where you have imidazole unit. Again this is your hard block and this is your soft block because of this long chain. In the soft block at the end you have imidazole unit which can interact with metal ions. So, if you add metal salts, say in this case zinc trifluoride they are adding, and from the solution you evaporate the solvent, then you can create this kind of material where you have a soft matrix which is basically cross linked by your hard backbone of the styrene, and then you can again create what you call as thermoplastic elastomeric materials. So, this then concludes our discussion on leaving radical polymerization. So, we will leave the radical polymerization behind, and in the next class we are going to start talking about the design principles of chemical reactors. So, till then, thank you and goodbye.